All right, let me know when you go
I think we're
live.
live.
Okay. See.
We good?
Yep, we're live.
All right. Hello and welcome to Corecast. I am your host, Tim.
And I'm Sahil. Welcome everybody to a brand new exciting episode of Courtcast. Before we get started, if you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to it. Without further ado, let's get to it. Also, if you another logistical thing, we're in the process of putting together shorts that will be releasing in soon. So if there's a certain topic that you'd like Tim and I to cover in a short, like a 1 minute soundbite, just let us know, and we'd be happy to consider that. So, all right. So now, without further ado, let's get to it. So, Tim, last time we had, someone is saying there's an echo.
There is echo. There should not be an echo.
Uh, yeah, saying there's an echo.
I'm not sure. Hold on 1 second. I'm not sure.
I think you have two windows open. Chat, can you let us know who has the echo? Is it me or Tim?
I'm not seeing it.
One of them is saying we're not hearing any echo. I'm not hearing any echo. So
Sahil, can you check? Echo, we can.
I don't hear any echo on my side. It's saying from both of us there's an echo.
Ah,
Oh, now it's okay.
I did not make any
Yeah, okay. I
changes.
think I think we're okay. If people continue to say it, we can see. Oh, apparently I have an echo.
I mean, that is, well, apologies for technical difficulties. Sahil, if you check the stream, you do not hear an echo, do you?
Yeah, I don't. I think I'm okay. Yeah, let's just okay. All right, we're good. We're good now. Let's just continue.
Okay. Yeah.
Okay. So apologies for that. A few people in the chat were saying we had an echo, but it seems like it's disappeared. Okay. So in our previous episode, we basically talked about how we observed that space-time has four dimensions, and we inquired about the possibility about what if there were less number of dimensions. So for a deep dive into that, do check out our previous episode. Um, and so here we wanted to talk about the other case. What if there's like more number of dimensions, for instance? And so I guess Tim, can you recap like what a dimension is and essentially what we're trying to get across?
Yeah, so I think previously we first defined what a dimension was, and dimension is basically the amount of freedom you have to move around, and also there's a symmetry aspect. And then we talk about what happens in lower dimensional situations, and we realize that in lower dimensions, there's it seems that below four perhaps there just isn't enough freedom to move around, and that is why maybe our space-time doesn't have lower dimensions. So 4 seems to be sort of the beginning of having enough dimensions to move around and have interesting things happen. Now, we move on to Now, so now we move on to higher dimensions. The question is, why not have more dimensions, like 5 or 6 or 7? And I think it turns out that it's plausible, but there are also other physics considerations which we'll discuss. And maybe because of that, 4 dimensions may be kind of like a Goldilocks dimensions, and that is why our universe chose to have 4. We'll go into more details that.
Yeah, yeah, yeah. So I guess like you know, so one thing we know is that we don't see these extra dimensions. We observe like 4 dimensions. And so my question is like, if there are extra dimensions, where are these dimensions?
So, I think one thing we need to clarify is that let's look at observation. Observationally, we do live in 4-dimensional world. There's no way around it because imagine I have a hand. My hand can only explore up, down, front, back, left, right. You know, if there are extra dimensions, there needs to be some reason why they are inaccessible. So minimally, we can say that the accessible number of dimensions is definitively 4, right? So, but then there's a question remains: could there be more dimensions that maybe for some reason are inaccessible? Now that is actually plausible.
Hmm. So so then I guess like so what you're saying is, wait, Tim, right, you can hear me, right?
Yes, I can hear you. Yeah.
Okay, sorry, you just cut off a little bit. Um, so what you're saying is that it's plausible there can be more than 4 dimensions. Could you repeat again? Could you restate what you're trying to say again? I didn't quite fully understand.
Yeah. So I would say that there could be more than 4 dimensions, but from observations, only 4 are accessible. So the extra ones has to be inaccessible in some ways. Um, so just because we can't access it, that we can't see it, doesn't mean it doesn't exist. But if we accept the fact that there could be extra dimensions, we need to explain why those are not accessible, basically.
Yeah, so then what is the explanation that they could like if you can't see them? I mean, by see, I'm assuming you mean even experimentally, like we don't really see them. So is it just a question of resolution, or is it by resolution, I mean like do we have to go at like smaller distance scales, higher energy, like build a better collider in that sense, or is it just something that like in principle you can't even really know, or is it just like a mathematical thing at the end
Yeah.
of the day?
Yeah, I would say that if in principle we can't access it, then the extra dimension doesn't exist, right? Like, because after all, we're talking about physics. Like, if we talk about
Mhm.
potential extra dimensions, it has to be accessible in some way, and maybe we couldn't access it yet. But so far, I'm just talking about plausibility. Like, it's plausible. Like in physics, there are many things that are plausible. It doesn't mean too much, but at least it does. It means that it's not crazy to consider extra dimensions, right?
Yeah, yeah. So, actually, I mean, my question is, why do we even need to consider extra dimensions? Like we see four. I mean, yeah, I know physics is not complete, but like, why is there a need to create like more dimensions than what we observe? Like, what purpose does that serve?
Yeah, I mean that is a great question, and some people might, I know some of the audience might have heard about popular science. Let's say talking about string theory, predicted 11 dimensions, 10 dimensions, whatever, and then they're just like, well, that sounds crazy. I only see 4 dimensions. Why do we even need these extra dimensions? That seems silly, right?
Mhm.
Like if the mathematics isn't broken, like why have extra dimensions? I think that's a fair perspective, but the reason why I think that's interesting. I think traces back, maybe not all the way back, but um, like Einstein back in the days had a dream of unification. When Einstein was thinking about gravity, he thinks about how gravity feels very similar to electromagnetism. And remember,
Mhm.
in previous episode, we said that depending on the number of dimensions, the amount of gravity kind of increases because gravity tells space-time, how it stretches in what direction, right? So if you count the number of particles, graviton, there are actually multiple types of graviton that does that. But if you go to higher dimensions, it turns out that you have more and more types of gravitons. And Einstein kind of came to this very intriguing. Actually, I guess my history is probably a little rusty. I'm not sure if it's Einstein or exactly, but at least physicists realize that, hey, look, if we have higher dimensions, we have more number of gravitons. Now, the dream would be that, is there some type of way that maybe every particle we see is some type of graviton? And initially, there was some success. This is called the Kaluza-Klein model, I think named after the physicist. So they realized that if let's say I take gravity in 5 dimension and do something very funny to that extra dimensions, you get something like gravity and electromagnetism. It's not exactly the same, it doesn't apply to our world, but you get something like it. And so that's why physicists are very interested in thinking about extra dimension, because like our world looks kind of sophisticated. There are many different types of particles, and maybe by going to a higher dimensional world, things could simplify, things could unify. So it's a very intriguing perspective.
So one question I have is like, can you explain what you mean by like different gravitons? I mean, we don't have to go super deep into that, but like, what does it mean to have like a different graviton? Like
Right.
increasing the number of gravitons.
Right, yeah. So the most familiar notion is probably light polarization. There are actually 2 types of light, and when you wear polarized sunglasses, and there's a difference between wearing just a pair of sunglasses and polarized sunglasses. The difference is polarized sunglasses filter a particular type of light that has a certain orientation, right? And gravity behaves the same way. And then you can ask, well, why is that necessary? But intuitively, it makes sense because ultimately gravity is the curvature of space-time. And in order for you to tell space and time how to curve, you have to look at which direction is curving. I mean, just kind of like imagine, I don't know, making bread. You're kneading the dough, right? You can stretch the dough and pull in different directions. So gravity, within a graviton, there needs to be instruction on like which direction to pull. And you can imagine the more dimensions you have, the more ways you can knead the space-time dough. So then there are more gravitons that exist.
So that makes sense. So you're saying that there's more flexibility in like what a graviton can be, and essentially you can create like different versions of them. My question is how does that lead to the idea of unification? Like, why, if there's more like gravitons, does that mean there's more unification? It just seems like your structure is getting more complicated the more dimensions you introduce. Like, seems like you're moving further away from unification.
Right, exactly. So, and the thing is, we have to kind of look at unification in kind of historically, right? For example, previously we thought electromagnetism and the weak force. The weak force is responsible for nuclear decay, and I think we may have another episode for that previously. Previously, people thought they were completely different things. But Weinberg and other physicists, I'm doing a terrible job citing different physicists, but they realized that by creating a bigger structure, they can accommodate electricity and electromagnetism and the weak force. And now they've been unified in the electroweak forces. And also they have to add in the extra complication, the Higgs boson, right? They need to add in the Higgs field. So before the Higgs boson was discovered, it seems like, oh man, that seems complicated, right? Like you add some extra stuff, they're like, how is that any better? Well, it turned out to be true. The whole thing is unified, and we see the Higgs boson. And that's why, even though it's true that if you go to high dimension, let's say you try to unify electromagnetism with gravity, you go to high dimension, you will get more than you bargained for. You get gravity, electromagnetism, and some other extra stuff. It might look crazy in the beginning, but hey, look, historically, things that seems crazy in the beginning turn out to be true. So I think it's fair to say that this at least is a worthwhile direction to pursue.
Yeah, that is interesting. So you're saying that if you have more dimensions, that introduces like a bigger structure that you can embed these phenomena that people think are different into like one unified framework. So in the case of electroweak, you take these two separate forces and you actually say they're part of, in fact, the same structure. And this you can do when you look at electromagnetism and gravity. If you introduce one extra dimension, then you can say, oh, these are actually part of the same thing. Is that at least what Einstein was doing? Is that my understanding correct on that?
Yeah, at least that was the hope. I mean, of course, it turned out that you couldn't exactly quite do that, and you can argue
Uh-huh.
that string theory is the more it's pretty much string theory is the much more glorified attempt to do that, and people have had
Mhm.
some success. But anyway, like yeah, the grand idea is there.
Gotcha. That makes sense. So I guess then like what makes these extra dimensions different than the ones that we have our regular four dimensions? Like, yeah, just what is the separation between the two in your mind?
Right. So of course, now let's if we accept the idea that let's say there were six dimensions and two of them were hidden. The natural
Hmm.
question is, what the heck? Why are these two dimensions hidden? Because remember, previously we said that we don't live in a piece of metal. All the
Yeah.
dimensions are created equal. That's the whole point of
Hmm.
dimensions, right? They're not different in any way. Like just like up, down, left, right, front, back are equal.
Hmm.
These large dimensions that we can explore should be in some ways identical to the dimensions that are hidden. But then the dimensions are hidden, like they are different. So so in some sense, you're shifting the problem. Let's say you use extra dimension to explain something. You are shifting the problem now. The problem becomes explaining, well, why these there are X dimensions that are hidden. But it's actually not too crazy. We can kind of use quantum mechanics to explain some of it, but maybe not all of it. But at least some of it has an explanation.
Hmm. So I guess okay. So what one other thing that comes to mind is like you mentioned string theory and like I think string theory is notorious for most people's minds of like introducing extra dimensions. I remember there are different string theories, one with 26 dimensions, one with this number of dimensions, and then eventually there's I think when the dust got settled, it became 11 dimensions. You probably know the history better than I do. So if string theory says there are 11 dimensions, but we observed four, how has it been whittled down to like four? Why not five or six? Like what what is actually special about four? And answering this, I'm really asking what is special about the number four?
I think at the crux of it, we at the end of the day, we don't exactly have a clue, but we have some hints, right?
Mm,
Um, so we know that maybe lower than four, it's not plausible. So
hmm.
maybe so you can say, oh, let's say we believe in string theory. There are 11 dimensions, a superstring theory anyway. And you say, well, why don't string theory create a world that's three dimensional, like two plus one, let's say? Well, you say
Mm,
maybe because if we don't have enough dimensions, like galaxies and humans wouldn't be able to thrive. That's fair, right?
hmm.
And then you can
Hmm.
say, well, why don't our universe become five dimensional, right? And it turns out that five dimensional universe could be quite reasonable. Um, but it could be that because the dimensions are larger, things get a little more complicated. And we'll explain
Hmm.
in a little bit why. And this extra complication could sway, like, life would become quite a bit harder, maybe for science or for complex structure to thrive. Maybe we don't exactly know if that's true yet. But that these two kind of competing forces, the amount of freedom that you're allowed to, the amount of freedom that you have to create interesting things, versus maybe there's too much freedom, things get too complicated. Four might
Hmm.
be this kind of Goldilocks zone in such a way that, and that's the universe that we live in.
Mhm. So could you say that like if you have less number of dimensions, then you say there are more restrictions on the system? So it's kind of this balance between like too many restrictions or not enough restrictions, and maybe four just happens to be that Goldilocks number of like just the right amount. Is that essentially what you're saying?
Yeah, kind of. And remember, this is not exact science, right? This is not like it's a little bit like looking for exoplanets. Like why is the
Hmm.
Earth this distance from the sun?
Hmm.
Well, if the Earth is a little too close to the sun, maybe oceans will boil, and maybe if it's a little
Hmm.
too far, it'll become a frozen planet. Of
Yeah.
course, we can't definitively say that life wouldn't exist if the Earth is really a little further, but at least we have some explanation, maybe.
Hmm.
I mean, it's almost like after the fact explanation, right? Because we live on Earth, we can explain why the Earth is this distance from the sun, and in a similar vein, maybe we can use that as an
Hmm.
explanation for why our world is four-dimensional.
Hmm. Yeah, so let's get into it. So, I mean, what happens when you okay, we discussed in the previous episode what happens when you have less number of dimensions and explain the different restrictions. Some forces probably won't even be there, or actually not probably, but won't actually be there in like in a when you have too few dimensions. Now, let's go on the other side. So, if I increase the number of dimensions, what's the big deal? Like, why is that a problem? Like, what problem does physics have with that besides just it not matching up experimentally? Like, is there a deeper thing? You're alluding to that.
Yeah. So one problem is it's a little bit technical, and one problem is comes from what we call quantum corrections. Um, so I think in a few episodes back we described in more details what quantum corrections are. But roughly speaking, you can think of our fundamental world is quantum mechanical, and the
Hmm.
quantum mechanical world is very violent, right? Things are coming in and out, popping in and out of existence. So it's a wonder that somehow our world looks smooth. Like I can talk to you, my hand is not just popping in and out, having a nuclear meltdown every other second, right? That would be terrible, right, for humans to live.
Hmm.
So somehow these quantum corrections are kind of canceled out and manageable. And and at the end of the day, we have a sort of predictable universe that we can operate in, that we can run experiments, run around. We know the sun is going to rise up tomorrow, and all that good stuff, right?
Hmm.
That all hinges on the fact that quantum corrections are not totally out of control, that the behaves predictably. And it
Hmm.
turns out that if you change the number of dimensions, because there's more freedom, there's also more quantum corrections, right? And it gets harder and harder to cancel those quantum corrections away. And this is a very technical term. And there's a technical word called renormalization. But roughly speaking, it's just how much control we have on a theory. And it turns out the higher the dimensions, the less controllable it is.
Hmm.
And it turns out that 4 is kind of in a little bit of a Goldilocks zone. Like it's not, the quantum corrections are not so crazy that the theories are really hard to deal with, but just okay enough that we have like you have electromagnetism and chemistry that are reasonable.
Okay. So I want to dig a little bit deep into this. So I mean, you mentioned the word quantum correction. Can we give a more intuitive sense of like what that is? So is that essentially that like a quantum correction? Could you think of it like as like a fluctuation or like something they're trying to account for? Yeah, I want to think of what's a different way of like an analogy maybe of what a quantum correction is.
Right.
Because it's not something that seems like nature is not correcting itself. It's just things are happening, but corrections seem to be things that we're imposing upon nature. So want to really frame it in that way. Like what is a quantum correction? Like experimentally, what does that even mean?
Right, and you're absolutely correct that nature does not care about quantum correction. I mean, it's almost like a made up term. So what is quantum correction? Quantum correction is just our way of saying that we try to predict something, but
Mhm.
somehow the result doesn't match what we see. There's a little bit of error. You can loosely think of it this way.
Mhm.
Um, so so the way physics works, at least in particle physics, is that particle physics is incomplete. We don't have the
Mhm.
full mathematical tool to predict everything. So the way it works is this. Imagine, let's take a concrete example. Let's take two electrons.
Mhm.
We can smash two electrons together and see what happens, right? And repeat. There's some
Mhm.
consistency the way two electrons smash into one another. It turns out that we can use the behavior of two electrons to kind of predict what happens when we smash three electrons together, four electrons together, and five electrons together. We can extrapolate, right? And this is sort of the crux of physics, right? I can use a simple process to predict a more complicated process, but then that prediction and okay, let's say I use two electrons to predict what happens when I smash three electrons together, right?
Mhm.
And that prediction and actually going to the lab and doing it, there might be a gap, right? It turns out that in 4 dimension, that gap is very under control. Like this is the realms of quantum correction, right? What I predict and what I see, probably the gap is under control. My theory is okay. In higher
Mhm.
dimensions, that gap could be out of control, it turns out. And
Mhm.
so it makes it harder and harder to make predictions out of the theory. And at some point, the theory becomes kind of useless, basically.
I see. I see. So let's take the case of like electromagnetism, for instance. So say you're trying to, predict certain properties of particles. You throw a light at like a particle and does something, it scatters, and you're trying to observe you're trying to compute some quantity, maybe the charge of an electron, the mass of an electron, or, some other property, and you do some experiment. And then what you're saying is that like in 4 dimensions, I don't need to like account for like many different anomalous events because those will all just in the theory will all magically cancel each other out. So I only need to worry about like a few like leading order effects, or like is that the way of thinking about it? Or
Yeah, sort of.
yeah.
I think an analogy may be more helpful. Like, so
Okay.
so one analogy I like to use is stock. It turns out that particle physics and stock market, at least the mathematics of it, has some similarity. So this is actually not a terrible analogy, right? Um, so imagine stock market. Let's say you have your favorite stock. Stock goes up. Let's say, like a nice theory would be like, hey, look, stock has been going up for the past 20 years. It's probably gonna go up in the next 10 years, right? And if you go
Mhm.
buy stock, you find out that, hey, look, stock goes up in the next 10 years. That's a good theory. That's like your renormalizable theory, right?
Okay.
A bad theory would be like, hey, look, stock goes up in the previous 20 years, but in the next 10 years, there's no information. It could go up or down, right? So in order to patch up your theory, you have to be like, well, guess what? The next 10 years is different. So I'm going to add these quantum corrections to be like, guess what? Oh, let's say my prediction originally was, hey, stock, next 10 years, stock goes up. And then I found out that stock didn't go up. I'll just add a quantum correction and be like, well, guess what? If stock goes up plus a correction means it goes down. And the next 10 years, I
Hmm.
have to do the same thing, right? Now, if you think of it this way, your stock model is complete garbage because it goes up or
Hmm.
down. You just add a correction that can match any results. So the idea of renormalizability is sort of like that, right?
Hmm. That makes sense. So what you're saying is that like if you go to high, so if we take it back to the how we started this conversation, if you add in more number of dimensions, it means that your theory is less, as you as you use the term renormalizable. And what that means is that your theory has a harder time predicting what will happen. So essentially, is it technically correct to say the more dimensions there are, the more chaotic things are, or is that not correct?
It is still. I wouldn't say it's chaotic. Like
Okay.
this analogy holds. Like for example, let's say I hit electrons at 200 units of energy, right?
Hmm.
I can extrapolate what would happen. Keep in mind the Stark
Hmm.
analogy. What would happen at 300 units of energy, right?
Hmm.
I can do that very well at 4 dimensions. But
Hmm.
if the world was 5 dimension, it gets harder.
Hmm.
Like maybe the results will be drastically different. There are these quantum corrections. And if I go to
Hmm.
6 dimension, that will get even worse. Worse and worse and worse and worse. Right? So this is kind of the
I,
level
s-
of predictability.
I see. I see. So, another analogy that comes to mind with this, could we think of dimensions in terms of stocks being like if you had one stock and that was the only, let's say, company that existed in the world, it's easier. I mean, still difficult, but it's still relatively easier to predict how it's going to move if it's just by itself. But if you start introducing like other stocks, these other stocks can interact with each other and they can move in like different ways. So the movement becomes harder to predict in a sense, loosely speaking. Is that a reasonable analogy, would
Yeah,
you
I'm
say?
not. Maybe not. I have to think about that.
Okay.
But
All right. I guess we can only take this analogy so far. I mean, there's
yeah,
also correlation. So if things are correlated, then maybe it's easier. I don't know. I mean, yeah, there's maybe more nuance. Okay, we don't have to take this analogy that far. Um, a- anyway, so okay, so we've talked about these quantum corrections being under control if you have fewer number of dimensions. Um, Let's talk. Okay, so that's with electromagnetism, and I'm assuming all the other force, the other two forces, strong and weak. But gravity is notoriously still difficult to do that. It's still even in 4 dimensions, it's still like out of control in terms of these quantum corrections. So can you give like a high or as you would call it, technically speaking, non-renormalizable? So what distinguishes gravity from the other forces? I mean, they're forces, so like why is gravity different at like a deep level?
yeah, gravity is notoriously different, and in order for gravity to be under control, I think you have to go to maybe 2 plus 1 dimension, like 2 dimension. But don't
Mhm.
take my word for it. I don't exactly remember the number, but
I see.
the reason gravity is difficult because gravity is universal, and it's universally attractive, at least in the most basic version of it. It means
Mhm.
that when you have, let's say you have two graviton hitting, let's say you're able to build a collider, smash two gravitons together. Let's say you're trying to
Mhm.
do that to extrapolate. Well, what happens if I collide gravitons at high energy or more gravitons, right? This is kind
Mhm.
of the extrapolation game, the analogy that we were talking earlier, like stock, right?
Mhm.
Extrapolating. Well, if you go at higher energy, that extra energy itself can gravitate. So it's almost like when you add more, there's a more compounding effect, right? So that prediction becomes harder and harder, and that compounding effect involves quantum gravity. Um, so it gets harder and harder, and so there's very little control in quantum gravity. So you really can't use what happens if you scatter two gravitons together to predict, uh, at least in great accuracy, what happens when you do it at higher energy or more gravitons.
Mhm. I see. I see. So basically scattering two gravitons, at least based on the way it's currently formulated, will really not tell you much about what happens if you get higher energy or if there's more involved,
Yeah,
essentially.
yeah, exactly. Because like for other
Mhm.
forces, it's different because there's a little bit more cancellation between the quantum corrections. For example,
Mhm.
electromagnetism, there are positive and negative charges. They kind of cancel each other out. Particles and
Mhm.
antiparticles, there's a little bit of cancellation. Yeah.
Mhm.
And also energy itself would not have electromagnetic charges, right? Like just because you have more energy does not mean that that extra energy will I don't know, irradiate electromagnetic field. Like it doesn't do that, you know. But
Mm.
gravity
But
has
if you,
this.
yeah.
Yep.
Oh, go ahead. Sorry. Go ahead.
Right. Yeah. Basically, gravity has this sort of self-enforcing behavior, and that just kind of explodes upon itself, you know.
So what you're saying is if you were to do an experiment at higher energy with gravitons, that higher energy may produce more gravitons because energy has, is the more energy you have, like, I guess more gravity there is, or I don't know the right term, but it'll interact more with gravity versus higher energy doesn't imply that there'll like be more electromagnetism involved, for instance, but gravity will just always be there.
Yeah. Yeah. So I mean, this is not completely black and white, right? You know, it's that
Mhm.
gravity is just less, using the technical term, gravity is less renormalizable. You know, it's a bit of a gradient, right? Gravity has
Mhm.
this self-enforcing effect, and it makes it trickier.
Mhm. I see. Um, so then, like, we talked about string theory as, coming back to it, string theory as being like this approach of unifying things and putting like a structure. But it seems like it just makes, I don't know, at least based on like our discussion so far, it seems like at first glance it'd make things worse. It like introduces more dimensions. And you mentioned if you introduce more dimensions, things get more out of control. And gravity is already out of control. So if you're introducing more dimensions and you're trying to incorporate gravity in your theory, why doesn't it all just break down? Like what's holding this together?
Right. So I think one thing we have to realize is that currently, like all this discussion about renormalizability and whatnot, is a little bit of
Mhm.
artifact, although not totally so. It tells you about our ability to extrapolate physics, right? Like you measure one thing, you extrapolate to another thing. And string theory is a little bit different because if you have a complete theory, you don't need to extrapolate anymore. And this is a difference between like let's take the stock let's kind of take the stock analogy further, right? You know, like
Mhm.
our model of physics is basically like these stock guru on YouTube just be like, hey, it's gonna go up or down. You know, maybe it works, maybe it doesn't. Well, although science
Yeah.
it is a little bit better than that. You know, it's not 50-50, right? But it's kind of like
Mhm.
that. But if you are string theory, it's almost like you have insider knowledge. You know all the inner
Mhm.
workings of everything, right? What string theory
Mhm.
does is instead of letting you extrapolate, well, let's just preface like if, in principle, right? Because string theory is also very hard to calculate things. But imagine you were able to work through the math and calculate things. It will show you that look, um, it will tell you in wholesale all the interactions term by term, like two graviton, three graviton, four graviton, six graviton,
Mhm.
all the possible in one go. So there's no need to extrapolate anymore. And that kind of resolves this problem where you are trying to
Mhm.
um, use an experiment to extrapolate further. So you don't need to do that. And I think string theory, I think you can safely say that that's the only theory that's able to do that, right?
Mhm. That that makes sense. Um, so okay, so you don't have to extrapolate further, but I guess like okay, so it introduces extra dimensions. Where are these extra dimensions? Coming back to like I think the first question I asked at the beginning of this, like where does string theory say extra dimensions live?
Yeah. So so theoretically, these extra dimensions are needed for this cancellation to happen, so that everything kind of add up together, right? Ultimately,
Mhm.
but yes, these dimensions have to be hidden, um, and you know, the only way to hide something, I think, is to make them inaccessible universally, and to do that in quantum physics, you know, probably you can guess now. To make things inaccessible, you make them small, and in quantum physics, there's this
Mhm.
relationship between the size of something and how much energy
Mhm.
you need to access it, right? Because
Mhm.
we know that in our experiments, there's an energy limit. The sun can only output so much, right? Fossil fuel can only output so much. So we're not able to reach certain kinds of energy yet. It could be that these extra dimensions are require so much energy for us to punch through, to kind of wiggle out of. That's why we haven't seen them yet.
Mm-hmm. So what you're saying is that these extra dimensions are really, really small, so they're universally inaccessible because um let me just ask this, like, what if you had the case where, like, in some part of the universe, whether it be part of the observable or unobservable, like these dimensions were more prominent, and then in other parts they were not as prominent, would they be dimensions, or like yeah, what if the size like fluctuated, for instance, of the dimension? You go like
It,
from one part of the universe to another.
it is plausible. So you have to understand first, what does it mean when I walk into when let's say I move my hand into these extra dimensions? What does it mean, right?
Mm-hmm.
If you believe the unification story, it means that literally, if my hand like slightly move into this extra dimension, first of all, I had to put in a lot of energy, right? The particle content of my hand will change. Like the electrons will become, I don't know, excited versions of the electron, or we probably give them a different name, right? And a nuclear reaction will happen, yeah? And then there will be a lot of energy. Well, I'll probably die, first of all. Like, there's a nuclear explosion that would not be pleasant for anybody.
Yeah.
So could we have something like that in the cosmos? It's plausible, actually. There could be what we call cosmic defects. Maybe really far out in the universe, this extra dimension chain sort of had some twists and turns and slight modification to it. And then you see a lot of energy, like maybe particle production in those areas and so forth. Or maybe we only see that in the past. Maybe that's no longer true. Maybe in the past, those extra dimensions were different. But then it will need a lot of energy to maintain that. And that energy will cause decay to different particles. And maybe we'll see a lot of extra galaxies, let's say in one directions, right? So cosmologists, well, I guess astronomers, astrophysicists have looked for these anomalies, these statistical patterns in the universe to see if there are maybe like a line, maybe like a line of overdensity in some direction in the universe, or maybe like a circle. I don't know, depending on how patterns are. We haven't been able to haven't been able to see that yet. It doesn't mean that it doesn't exist. It could just be that they're really far away, right?
Okay, so I guess so if these dimensions were like, let's say, extremely large, like super, just insanely, unimaginably huge, that, like, I don't know, what would that mean?
Well, experimentally, that can't possibly be true, but let's entertain the idea that that is true. That means that I don't need a lot of energy to just walk into them, right? Like, imagine how I can move my hand using my muscle. I can just move front, back, up, down, left, right. Maybe these dimensions are not so large, so that I might just maybe flick my thumb and my thumb will go into this extra dimension for a little bit, right? Maybe I'll feel a little bit of tickle, right? I don't know. It will emit some light. My fingers will light up, right? Of course, for a dimension that's super large, I would just be able to swim in it. It will feel so intuitive. Probably the Earth will have to be a high dimensional sphere, right? It would just, the Earth will be really weird, I guess. Instead of like your GPS navigation will have to have more coordinates. That would be kind of weird. Depending on how large,
I see.
Right? The size does matter.
Gotcha. So then if we say these, like, dimensions are like really, really small, is there any way to really, like, test for them? Like, what would it take, Tim, to convince you that extra dimensions exist unequivocally?
I think first of all, we need to find something new. What I mean by that, if there is an extra dimension, then
Hmm.
some particle somewhere must be able to gather enough energy to move in that direction. Yeah. And
Hmm.
I think in a few episodes back, we give the analogy of like, this extra dimension is like you're stuck in a bus, right? Like you're trying to wiggle your way out. Like for some particle, it might be easier for them to wiggle out than others.
Hmm.
You know,
Hmm.
we will first have to see that, hey, look, let's take an electron. Can we shoot enough energy for it to wiggle in such a way that it can do something, right? To
Hmm.
see maybe like a wiggled version of the electron, which will probably decay in a little bit, radiate a lot of light and energy back, right? So we'll first see that. But that wouldn't confirm extra dimension yet, right? Because extra
Hmm.
dimension, remember, has to be universal. So if an electron can do it, like a
Hmm.
proton should be able to do it too, or the quarks within a proton. So we should
Yeah.
see the same thing for different particles. First for the electron and
Hmm.
then for the other particles. Um,
Hmm.
of course, you can build a theoretical model where the interaction between different particles and this extra dimension might have a little bit of a subtle difference, right? It could be because of the way the extra dimensions are. It's plausible, but for the most part, they need to be universal. Like if I can access it, Sahil, you should be able to access it. I mean, it needs to be
Hmm.
democratic, right? Like our listeners should be able to access it. Anyone should be able to access it. I mean, this is true democracy, I would say. Like so
I see.
so that the universality of it, after
Hmm.
discovering something new, will be the way to fully convince someone that there's universal extra dimension.
So would it be like, because it's hard. I mean, I think it's hard for anyone to conceptualize this, but like with these extra dimensions, every experiment we do, we would, need to translate it back into like the four dimensions that we currently live in. So like let's say I do an experiment and I somehow observe extra dimensions. If I'm to tell you those results, it needs to be stated in the four dimensions that we live in because you weren't there for the experiment. So what would I like see, or like I don't know, what would it be? Would it just be like particles transforming into something like completely new that's like unexplained by any of the conservation laws that we have, or like yeah, just like what would that be?
I mean, I don't think it'll be that dramatic, right? Like
Uh-huh.
of course, given the current status of physics, these extra
Hmm.
dimensions will have to be super duper tiny. And to
Yeah.
access them, the minimum you need is to start a nuclear reaction, right? So these extra dimensions are completely unrecognizable to any other dimension that we know and love, right? Like going
Hmm.
going going to the mall, I have to move in the normal dimensions, and I don't start a nuclear reaction. But going to the extra
Hmm.
dimensions, I will have to start a nuclear reaction. But it
Yeah.
right, but in a so if we discover the realistic type of extra dimensions, I
Hmm.
don't think our everyday life would change very much, right? This is very limited. Only in very limited cases will we see these effects. Um, but if we
What?
imagine a hypothetical world where
Hmm.
these large extra dimensions are more accessible, right?
Hmm.
Let's say large-ish, maybe not super large, like as large as the
Hmm.
universe, but like I don't know, maybe like a millimeter, maybe like uh, a kilometer or something, right? Like I should be
Yeah.
able to go on a walk in that extra dimension, but like it's gonna take me some energy. Maybe I have to, I don't know, like you know, really work hard. I don't know, it'll be a serious workout. But then I wouldn't start a nuclear reaction. Like maybe I'll radiate some
Yeah.
light. Probably I probably have to do some calculation. It might still not be good for your body. Like you have some radiation, but like
Uh-huh.
you have some radiation burn or whatever. But like you should be able to take a walk in it and feel like basically the particles in Tim will get excited as I walk in this extra dimension. As I pick up
Hmm.
momentum in that extra dimension, I should kind of feel it. And then the way I
Hmm.
see the world would be like, hey, look, I'm in this elevated. I don't even know how to explain it because like I'm trying my best, but like the like I wouldn't be that different if this extra dimension is large-ish. I'll just be like an excited version of Tim, and maybe I'll irradiate some light. Wouldn't be good for my
uh,
skin, but like I'll still survive, right?
but like, would you be able to like see it or like perceive it? I guess you'd be able to perceive it. I
Yeah,
guess it's unclear what it would even look like.
I think to be able to perceive it means that can light travel in this extra dimension reasonably? I think if it can,
Mm,
I mean, there's still some barrier, right? Like the light still has to
mm,
pick up some energy to travel to you. But if the extra dimension
mm.
is large-ish, maybe that's not too hard. Maybe you can see things. I don't know what that would look like.
That's fair. That's fair. Um, okay, so what I'm getting is that like these extra dimensions are really small. And I mean, when I was first introduced to this concept of extra dimensions, it just seemed to like be introduced to make like the math nice and to work out. Is that an actual like reason to like believe this, or yeah, it just seems more like a mathematical artifact in some sense.
Yeah, I think historically maybe that's kind of like that because
Mhm.
I think historically it's like, oh, why not? Because the math works for different dimensions, right?
Yeah.
But once you study physics, I think you realize that there are just so much diversity in
Hmm.
the type of particles, forces, and stuff in our universe.
Hmm.
And in some sense, there's not enough possibility in this low dimensional world to completely unify them. So I think if you truly believe in truly believe that everything is ultimately one and the same,
Hmm.
probably extra dimension will have to be part of the story.
Hmm. I see. I see. That is, yeah, that is interesting. Very difficult for me to perceive what that is, but I'm sure other people also may also have that issue. Um, we have an audience question. I mean, audience member mentions it might be too big of a question, but is asking, isn't energy an abstraction? If so, why is it a useful concept in physics?
No, that's actually a great question. So in some sense, if you really dig into the fundamentals of physics, because we talk about this a lot, because energy also ultimately is not conserved and yada and yada.
Hmm.
So fundamentally, yeah, maybe energy isn't the best concept, but from a practical standpoint, that's like at least in this episode, right? Like we're talking when you talk about extra dimension, there are a few ways to look at it. Practically, there are four dimensions. It's just true, you know.
Hmm.
When that's true, then if you start from that angle, then you probably will use all the practical concept that you have. Then you can say, well, from
Hmm.
this angle, why can't we access the other extra dimensions? Then energy makes sense in this universe, and then from the bottom up perspective, the dimensions are hidden because we don't have enough energy. So that's a useful concept. Of course, there probably isn't a good fundamental reason why energy is the barrier, why we couldn't access these extra dimensions. Like, yeah, I don't really have a. It's probably not a good explanation if that makes sense, right? Like, it
Hmm.
depends on what discussion you're trying to have. If you're trying to have a practical discussion, like why the universe is the way it is, then yes, you would use a concept that is practical for our world. And if you want to talk
Hmm.
about really fundamental stuff, where energy is not even conserved, and you're just talking about theories in general, um,
Hmm.
it is still you can elevate energy to something a little more. You can use a more generalized concept that energy is embedded in, like symmetry, to have these
Hmm.
discussion, um, but the utility sure will be a little bit reduced. Yeah.
Hmm. Yeah, that makes sense. All right, final question for you, Tim. Speculative. If you were to put money on like what the truth of the universe is, would you say there are fewer like dimensions or more dimensions? And by fewer dimensions, I don't mean like the spatial, but something a bit more abstract in some sense that like our four spatial dimensions, sorry, our three plus one dimensions, our space-time like emerges from something that's like has far fewer dimensions. Maybe even the extra dimensions emerge from this thing. Or do you think like it's just like the, end all be alls that there are more dimensions?
I mean, yeah, that's interesting. So kind of I guess wrapping up our previous few episodes.
Mm,
I think probably I would put money on having more dimensions. Um,
okay.
and I know if you think about fundamental physics, all of this discussion could be wrong. There could be something more fundamental, and the concept of
Mm,
dimensions, where the concept of dimension might not even make sense in that way. And then
mm,
maybe you can have holographic principles. Maybe the universe is a projection of some sort from a low dimensional thing, whatever. Um, but I'm a big sucker of freedom and and symmetry. And if you have more dimensions, you have more symmetry. So those go hand in hand, right? And you can think of dimensions as a manifestation of symmetry. I think if there's a concept that supersedes this concept of notion of dimension, I mean, let's face it, what is dimension? It's just how different ways you can move, right? And if you include particles, it's just different types of particles, right? And if you
yeah.
believe they're all one and the same, it's just the
Hmm.
amount of relationship you have, and it's just the size of your symmetry. And
Hmm.
so, let's bring it. Bring all the symmetries we can. There should be more and more symmetry. If you believe in a beautiful universe, I think it makes sense to put the money on having more dimensions, more symmetries, more freedom. Degrees of freedom, anyway.
Yeah, that is interesting. I kind of lean towards the opposite direction, but that can be a conversation for another day. So we're almost at time. So I wanted to, in our tradition, give you a chance to leave the audience with any words of wisdom that higher dimensions has taught you.
Yeah, I mean, I guess this is just a little bit of a reflection from the previous few episodes. It all started with why four. Four seemed
Hmm.
it's like such a special number. We
Hmm.
talk about why not less, why not more, and maybe at the
Hmm.
end of the day, all that doesn't matter. It could just be like, you know, it could be like the same thing about exoplanet, right? Um,
Hmm.
but but look, we have one universe. I mean, I think one can't help but be curious to wonder where does the number four come from. Maybe it's all meaningless. Maybe God roll a die and just 1, 2, 3, 4, 5, 6 and pick four, and we're stuck with it, right? Um, but yet, I think it's human nature. We can't help but wonder, and even at the end of the day, it doesn't make any sense. At least we uncover some really interesting stuff, right? Like, I know that the concept of dimension is kind of, I don't know what a 5-dimensional world looks like, or a 3-dimensional, or 2 plus 1 3-dimensional world looks like. But I don't know. You can't help but think we can't help but think that there's some significance, from this number four. So maybe we don't know the answer, but I hope to continue to learn and understand what, at least get a little bit of hint on what that is. So I think our episode hopefully give you some sense of that. It's still a big unknown, but maybe in the future we'll find out. Maybe aliens will tell us why in the next million years or something.
Yeah. Or yeah. That yeah. I definitely don't think it's gonna be in my lifetime for sure. I will find out why we live in four dimensions. But yeah, on that note, I want to thank everyone for joining us, and we'll see you all next week.
Yeah, see you all next week. Bye bye.
Bye.